1.1 Functions and their graphs. The outline of this video is as follows. We will discuss the core concepts of functions, starting with the fundamental definitions of a function, its domain, and its range. I will then introduce the vertical line test, a simple graphical method for identifying functions. After that, we will look at piecewise defined functions, which are built from different formulas on different parts of their domain. We will also learn to describe a function's behavior by identifying intervals where it is increasing or decreasing. Next, we will explore the concept of symmetry and how it relates to classifying functions as either even or odd. To wrap up, I will present a catalog of common function types, giving us a toolkit of examples that we will use throughout our studies. A function is a fundamental mathematical tool we use to describe how one quantity depends on another. The basic idea is that for many real-world situations, the value of one variable, like the area of a circle, is determined by the value of another, like its radius. We write this relationship using the notation y equals f of x. In this expression, the letter x is the input, which we call the independent variable. The symbol f represents the function itself, which is the specific rule that transforms the input. Finally, the letter y is the output, or the dependent variable, because its value depends on the input we chose for x. For instance, if our function is the rule for a circle's area, a specific radius we input will always produce one single predictable area as the output. In short, a function is simply a reliable rule that assigns exactly one output to every valid input. Let us establish the formal definition of a function, which is the fundamental rule that connects inputs to outputs. A function is a rule that assigns to each element x from an input set, called the domain, exactly one single output element, f of x, in a set y. As we consider all the possible inputs from the domain, the complete set of all the outputs we produce is called the range. For example, if a function squares a number, its domain can be all real numbers, but its range includes only the non-negative numbers, since a square is never negative. It is important not to confuse the range, which is the set of actual outputs, with the larger set y that contains it. The essential idea to remember is that a function provides a unique, predictable output for every single input from its domain. To build a strong intuition for what a function is, it helps to visualize it in a couple of ways. First, you can think of a function as a machine. You put in an input, which is an element from a set we call the domain, and the machine processes it to produce exactly one output. A second, similar idea is an arrow diagram, where an arrow connects each input from the domain to its unique corresponding output in another set. The most important rule for both visualizations is that a single input can never map to two different outputs. For example, if you press the square root key on a calculator with the input 9, it will always give you the single output 3, never 3, and also -3. Do not confuse this with the fact that different inputs, like 2 and -2, can both map to the same output, 4, when squared. The essential idea is that every input has one, and only one, predictable output. I will explain the concept of a natural domain, which is our essential starting point for understanding a function's inputs when they are not explicitly defined. The natural domain is the largest set of real input values, for which a formula produces real output values. For instance, the function y equals x squared can accept any real number, so its natural domain is the entire set of real numbers, from -infinity to +infinity. This, in turn, produces a range, or a set of outputs, of all numbers greater than or equal to 0. However, we can restrict the domain. If we specify that y equals x squared, but only for inputs x greater than or equal to 2, the range changes significantly. Now, the smallest possible output is 4, making the new range all numbers from 4 to infinity. The set of allowed inputs directly determines the set of possible outputs. Let us explore the concept of a function's natural domain and range, which is essential for understanding the set of all valid inputs and their corresponding outputs. The natural domain is the largest set of input values for which a formula produces a real, valid output when no other restrictions are given. For example, with the function y equals x squared, the domain is all real numbers because any number can be squared, while the range is only non-negative numbers. For the function y equals 1 over x, the domain must exclude 0, because division by 0 is undefined, which also means the range excludes 0. Finally, for y equals the square root of x, the domain is restricted to non-negative numbers, as the square root of a negative value is not a real number. Ultimately, the specific mathematical operations in a formula are what determine its natural domain and the resulting range. Let us continue finding natural domains by looking at two more functions involving square roots, which require us to ensure we always get a real number as an output. For the function y equals the square root of 4 minus x, the expression inside the root, which is 4 minus x, must be greater than or equal to 0. Solving this inequality tells us that x must be less than or equal to 4, which defines the domain. The resulting outputs, or the range, will be all non-negative numbers. Now consider y equals the square root of 1 minus x squared. Here, we need 1 minus x squared to be non-negative, which is only true when x is in the closed interval from -1 to 1. As x moves from -1 to +1, the output value starts at 0, rises to a maximum of 1, and returns to 0, making the range the closed interval from 0 to 1. Remember, the domain is the set of valid inputs, not the set of outputs. To find the natural domain of a square root function, simply set the expression inside the root to be greater than or equal to 0 and solve. We can visualize a function by creating its graph, which gives us a powerful picture of the relationship between its inputs and outputs. A function's graph is simply the set of all points, which we can call x, y, where each x is an input from the function's domain and each y is the corresponding output, f of x. This means that for any input x, the value f of x represents the vertical height of the graph at that position. For example, on the graph of y equals x squared, the point 2, 4 tells us the function's height is 4 when the input is 2. But this raises a key question. How can we be sure of the graph's shape between the points we plot? For now, we connect them as best we can, which is an educated guess. Ultimately, calculus will provide the definitive tools to understand the exact behavior of the curve everywhere. I find that representing a function numerically is one of the most practical methods, especially when working with data from the real world. Besides using formulas or graphs, we can define a function simply as a table of values, which is how data is often collected in science and engineering. If we plot these individual data points on a graph, the result is called a scatter plot, which is a collection of distinct points. The next logical step is to connect these points, usually with a smooth curve, to help us visualize the underlying relationship that the data describes. For example, a table could show air pressure measurements from a tuning fork over time. Plotting these points reveals the shape of the sound wave. Do not confuse the scatter plot itself with the full function, as connecting the points is our best guess at the continuous relationship. Ultimately, a table of values is a powerful way to represent a function when you begin with experimental measurements. I will show you a simple, visual way to check if a curve is the graph of a function, which we call the vertical line test. This works because the definition of a function requires that for every input x, there can be only one single output, f of x. To use this test, simply imagine a vertical line sweeping across the graph. If that line never touches the curve in more than one place at a time, then the curve is the graph of a function. But if you can find even one vertical line that intersects the curve at 2 or more points, it is not a function. A classic example is a circle, which fails the test. We can, however, represent a circle using 2 separate functions, one for the top semicircle and one for the bottom semicircle. So, the essential thing to remember is that a function's graph can only have one output for any single input. Let us explore piecewise defined functions, which are essential tools for modeling situations where the governing rule changes. A piecewise defined function is one that uses different formulas for different parts of its domain, which is the set of all possible inputs. A common example is the absolute value of x. This function has 2 pieces. If the input x is 0 or positive, the output is just x itself, but if the input x is negative, the output is negative x to make the result positive. We can also build functions with more than 2 pieces, like the function f of x shown here, which uses 3 different rules. For instance, to find the value at x equals 2, we see that 2 is greater than 1, so we use the third rule, and the result is simply 1. It is important to remember that even though it uses multiple formulas, this is still a single function. The main thing to remember is that, for any given input, only one of the formulas will apply. Let us explore 2 special piecewise functions, the floor and ceiling functions, which are useful for modeling situations that involve discrete steps or rounding. The first is the greatest integer function, commonly called the floor function, and written as y equals the floor of x. It gives the greatest integer that is less than or equal to its input. For example, the floor of 2.4 is 2, but be careful with negative numbers, as the floor of negative 1.2 is negative 2. The second function is the least integer function, or ceiling function, written as y equals the ceiling of x. This function does the opposite, providing the smallest integer that is greater than or equal to its input. You can think of a parking garage that charges for a full hour, even if you only stay for a fraction of it. In summary, the floor function always rounds the input down, while the ceiling function always rounds the input up. I want to formalize our intuitive idea of a function's graph rising or falling, which is essential for describing its overall behavior. We say a function is increasing on an interval, which is just a continuous stretch of the x-axis, if its value always gets larger as its input gets larger. In other words, as you move from left to right along the graph, you are always going uphill. A function is decreasing if the opposite is true. Its value always gets smaller as the input gets larger, so the graph is always going downhill. For instance, the example function shown is decreasing until it hits x equals 0. Then it is increasing until x equals 1. After that point, it becomes constant, which is a state that is neither increasing nor decreasing. The key is to remember that these terms describe whether the function's output consistently rises or falls over a specific interval. We can classify functions as even or odd based on their symmetry, which gives us a powerful shortcut for understanding their graphs. A function is called an even function if plugging in a negative input value gives you the exact same result as the positive input, so f of negative x equals f of x. This property means its graph is perfectly symmetric about the vertical y-axis, like a mirror image. For example, the function y equals x squared is an even function. On the other hand, a function is an odd function if f of negative x equals the negative of f of x. This results in a graph that is symmetric about the origin, meaning you could rotate it 180 degrees and it would look unchanged, like the function y equals x cubed. It is important to remember that many functions are neither even nor odd. This classification provides a quick algebraic test to determine the geometric symmetry of a function's graph. Let us begin by exploring 2 foundational families of functions, linear and power functions, which are essential building blocks for more complex models. First, A linear function is defined by the equation f of x equals m times x plus b, and its graph is always a straight line. The constant m is the slope, which measures the line's steepness, while the constant b is the y-intercept, telling us where the line crosses the vertical axis. The function's behavior is determined by its slope. If m is positive, the function is increasing. If m is negative, it is decreasing. And if m is 0, the line is horizontal, representing a constant function. The second family is the power function, which has the form f of x equals x to the power of a, where the exponent a is a constant. We will soon examine how the graph changes for integer, negative, and rational powers. Recognizing these two simple forms is the first step toward understanding more advanced functions. We will now look at power functions with positive integer exponents, which are important because the exponent's parity, whether it is even or odd, determines the graph's fundamental symmetry. The power function has the form f of x equals x to the power of n. When the exponent n is an even integer like 2 or 4, we get an even function, meaning its graph is symmetric across the y-axis like a mirror image. Conversely, when n is an odd integer like 1 or 3, we get an odd function, which has rotational symmetry about the origin. For a simple example, picture the y-u shape of y equals x squared, which is even, versus the s-curve of y equals x cubed, which is odd. For all these functions, as the power n increases, the graphs also become much steeper for inputs, with an absolute value greater than 1. The essential point to remember is that you can predict a graph's symmetry just by checking if its integer exponent is even or odd. Power functions with negative integer exponents are fundamental for modeling inverse relationships, like how pressure and volume are related. We write these functions as f of x equals x to the power of negative n, which is the same as 1 divided by x to the power of n. A critical point is that because division by 0 is undefined, these functions exist for all real numbers except when x is 0. For example, the function f of x equals 1 over x produces a graph called a hyperbola. As x gets extremely large, the value of 1 over x gets incredibly close to 0, but never touches it. This behavior of approaching a line without ever reaching it defines an asymptote, and here the coordinate axes act as asymptotes. So do not confuse the graph getting close to an axis with it ever crossing that axis. The key takeaway is that negative integer powers create graphs that are broken at x equals 0 and hug the axes. Let us explore power functions with fractional exponents, which we also call root functions, because their behavior depends critically on the type of root involved. A function's domain is simply the set of all its possible input values. I will start with the square root function, f of x equals x to the power of 1/2. Since we cannot take the square root of a negative number and get a real result, its domain is restricted to all non-negative numbers, or the interval from 0 to infinity. In contrast, consider the cube root function, f of x equals x to the power of 1/3. You can take the cube root of any number. For instance, the cube root of -8 is simply -2. This means its domain is all real numbers. So, do not confuse the behavior of even and odd roots. The essential point to remember is that even roots restrict the domain, while odd roots are defined for all real numbers. Let us explore polynomials, which are some of the most fundamental and useful functions in algebra. A polynomial is simply a function built by adding terms together, where each term consists of a constant number, which we call a coefficient, multiplied by a variable raised to a non-negative whole number power. The highest power of the variable that has a non-zero coefficient is called the degree of the polynomial, and this number tells us a lot about the function's behavior. For instance, a familiar quadratic function, like p of x equals a times x squared plus b times x plus c, is just a polynomial of degree 2. It is important not to confuse these with functions involving fractional or negative powers, such as the square root of x. Because they are constructed so simply, a key property to remember is that all polynomials are smooth, continuous functions whose domain covers all real numbers. Let us explore rational functions, which are incredibly useful for modeling complex relationships, but require us to pay close attention to their domains. A rational function is defined as a ratio of two polynomials, which I can write as f of x equals p of x divided by q of x. The most important rule for these functions comes from the fact that division by zero is undefined. Therefore, the function's domain, which is the set of all valid inputs, includes all real numbers except for any value of x that makes the denominator, q of x, equal to 0. This restriction is what gives their graphs such interesting shapes, often featuring breaks or approaching lines called asymptotes. For example, a function like 1 divided by the quantity x minus 2 is undefined at x equals 2. The key takeaway is that to find the domain of any rational function, you must first find and exclude the values that make its denominator 0. Beyond polynomials and rational functions, we have several other crucial classes of functions that model more complex behaviors. We can group these into two main types, which are algebraic and transcendental. Algebraic functions are any that are constructed from polynomials, using operations like addition, division, or taking roots. Any function that is not algebraic is called a transcendental function, a broad category that includes many important types. The most common examples are the periodic trigonometric functions like sine and cosine, exponential functions where the variable is in the exponent, such as f of x equals a to the power of x, and their inverses, the logarithmic functions. For instance, the gentle curve formed by a hanging telephone cable is the graph of a transcendental function. So remember that trigonometric and exponential functions are simply specific examples within the larger transcendental class. These new function classes give us a much richer toolkit for describing the world. Let us summarize the core concepts of functions, which are the fundamental building blocks for everything we will do in calculus. At its heart, a function is a rule that assigns a single, unique output to each input from a set called the domain, while the collection of all possible outputs is called the range. We can represent these rules in several ways, through equations, graphs, numerical tables, or even verbal descriptions. For graphs, we can use a simple tool called the vertical line test, which provides a quick visual check to confirm if a curve truly represents a function. We also characterize functions by their key properties, such as intervals of increase and decrease, or their symmetry, which we describe as being either even or odd. A solid understanding of these ideas and the common families of functions is the essential foundation for all of calculus. It is crucial to understand the difference between a function's natural domain and a restricted domain, as this distinction allows us to model the real world accurately. A function's natural domain includes every possible input value for which its formula produces a valid, real number output. In contrast, a restricted domain is one we deliberately limit to fit the specific constraints of a problem. For a concrete example, take the area of a circle, given by the formula A equals pi times r squared. Mathematically, the input r could be any real number, since any number can be squared. But because r represents a physical radius, which cannot be negative, we must restrict its domain to only positive values. The essential idea is that the context of a problem determines whether the full natural domain is appropriate, or if a more limited, restricted domain is necessary.